In this lesson, we'll look at parallel processing and do a deep dive into parallel processor systems. We'll be looking at four main types, and they are SISD, SIMD, MISD, and MIMD. Now, it's pretty common sense that if you have one processor, it will do one particular task. But if you have multiple processors, chances are you can subdivide that task and end up completing the task a lot more quickly. So that approach was taken in processor design, and as a result of that, we have quad-core, octa-core, and moving beyond that, we're going to have 12-core and 16-core processors, where on one single chip, we can create multiple CPU dies, which will mean that the processing is much more quicker than a single processor. However, we can go even beyond that, taking these octa-core processors and then having many of these octa-core processors, we can create a true parallel system. So we're going to be looking at the different ways or the different architecture styles that are used to create parallel processing systems. Now, before we begin, we're going to do a prior knowledge check. Do you remember what is meant by pipelining? What are the common stages of a fetch-execute cycle pipeline? How are interrupts handled in a RISC processor? And what is meant by parallel processing? So do pause the video and think about these and then continue when you're ready. Now, pipelining basically means that you're allowing several instructions to be processed simultaneously without having to wait for a previous instruction to finish. And the common stages of a fetch-execute pipeline are instruction fetch cycle, instruction decode cycle, operand fetch cycle, instruction execution cycle, and the write-back results process. How are interrupts handled in a RISC processor? Well, because you have a pipeline, what's going to happen is that normally the write-back stage is actually completed and all the other stages are put into registers and their status is saved. Once the interrupt is dealt with, those are then reloaded and the program continues from that part. And finally, what is meant by parallel processing? Parallel processing basically is the operations which allow a process to be split up and for each part to be executed by a different processor at the same time. So if you have one instruction, it could be divided into 4 parts and then 4 separate processors could run them at the same time. That means you complete that program or that process much more quicker compared to a conventional processor. Now, in this particular unit, there's a lot of acronyms, so I thought it would be useful for us to display the key terms. So do pause the video and jot these key terms down. You should be able to understand if in an exam SISC or RISC is mentioned, what is meant by pipelining and parallel processing. Similarly, SISD, SIMD, MISD, and MIMD. What's meant by cluster and what's meant by massively parallel computers. So do pause the video and jot these down and then continue when ready. Okay, we're just going to have a brief review of pipelining just in case you've forgotten about that from the previous lessons. Pipelining allows several instructions to be processed simultaneously without having to wait for previous instructions to be completed. And normally in an exam, you will be given something like this. So the stages will be given to you, which are instruction fetch cycle, decode cycle, operand fetch, instruction execution, and the write-back results process. And then you'd be given some clock cycles on the top, and you will be asked to split a task and ensure that it fits the pipeline. Task A will go for the fetch, and after that B will go for fetching, and then C and D and E and F. And that will depend on the context that they give you. So make sure that you're familiar with this particular diagram because your exam questions are going to be based on this. Now, similarly, you've got to be familiar with how interrupts could happen. And once the processor detects the existence of an interrupt, which is normally at the end of a fetch execute cycle, the current program would temporarily be stopped. Now, how does that work in that pipeline stages? Well, let's just say you got a new interrupt, let's just call it S, arriving at clock cycle 6. Now, the processor needs to make sure that FEDC, those instructions are stored in registers and only B is written. And after that, you'd probably put S in all of those. So the instruction fetch stage in 6 will be S. Then in 7, that will be the ID stage. In 8, that will be the OF stage. And in 9, it'll be the IE stage. And in 10, it will be the write-back stage. So once the interrupt handle routine services the interrupt, the processor can then reload all of those remaining instructions back from the registers into the pipeline. In an exam, you will probably be given an empty pipeline like this, and then you would need to make sure that you put the right instructions in the correct place in the pipeline. Now, there are four basic categories of computer architecture that are used when we are looking at either single processing or parallel processing. And the first one is SISD, which stands for Single Instruction, Single Data Processes. This architecture uses a single processor that can handle just one instruction, and it works on one data source at a time. So think about this. You might want to add something to the accumulator, so you will have one operand and one instruction. Each task is processed in a sequential order. So you go to the first instruction, then the next one. And since there is a single processor, this type of architecture does not allow for parallel processing at all. So this is normally found in early personal computers. Now, technically, you probably could do some parallel processing if you have multiple single processes running in parallel. However, that would require a lot of management to be done on the software side, breaking instructions down into multiple parts and making sure that the instruction sets can work with these 5-part instructions, and then stitching everything up together when you get the output. So as you probably have guessed, nobody thought this was a good idea, and these are only used for just single purpose sequential computers. Next up is SIMD, which stands for Single Instruction Multiple Data, and this uses many processors, and each processor executes the same instruction but uses different data inputs. They're all doing the same calculations but on different data at the same time. Now, SIMD are often referred to as array processors, and they have a particular application in graphics cards. For example, suppose you want to change the brightness of an image, which is made up of 4,000 pixels, and you want to increase it. Since SIMD can work on many data items at the same time, 4,000 small processors, one per pixel, can each alter the brightness of each of the pixels by the same amount at the same time. This means that the whole of the image will have its brightness increased consistently, rather than increase the first pixel, then move on to the next one, then move on to the next one. Other applications could include sound sampling, or any application where a large number of items need to be altered by the same amount, and since each processor is doing the same calculation on each data item, SIMD is the architecture that you will be using. And since you are working on every pixel at the same time, that's basically parallel processing. So multiple processors apply the same instruction on different data sources. Now, after that, we have MISD, which stands for Multiple Instruction Single Data, and that also uses several processors. However, each processor uses different instructions but shares the same data source. Now, think about this, that you might have one set of data, but you want to try different calculations on the same set of data. That's where MISD type processors were useful. However, MISD is not a commonly used architecture. MIMD tends to be used instead of this. The only use I can think of is the American Space Shuttle Flight Control System that used to use MISD processor, because you might have telemetry data coming in, which is just one set of data, and different instruments use that data differently. So you have different types of instructions being applied to the same data, and that could be useful in fuel calculations, navigation, all sorts of different purposes for that space shuttle program. However, MIMD has superseded this type of architecture. So very limited use, but it is a parallel processing architecture. And finally, we have MIMD, which stands for Multiple Instruction, Multiple Data, and this also uses multiple processors. However, the key difference here is that each processor can take a different instruction and then apply it to a different data source. So think about the previous ones. Sometimes you had one instruction applied to different data sources. Sometimes you have different instructions applied to the same data source. This one uses multiple instructions, so each one takes its instructions independently, and each processor can use data from a separate data source. Now, the data source may be a single memory unit which has been suitably partitioned, or separate data sources. The MIMD architecture is used in multi-core systems, for example, supercomputers, or in the architecture of multi-core chips like quad-core, octa-core chips that you commonly see in mobile phones and laptop computers these days. Now, before considering parallel processing, there are a number of factors to consider. For example, when carrying out parallel processing, processors need to be able to communicate. The data which has been processed needs to be transferred from one processor to another. And when software is being designed or a programming language is being chosen, they must be capable of processing data from multiple processes at the same time. If they're not, then parallel processing can't happen because you're going to have a bottleneck. Parallel processing is a much faster method for handling large volumes of independent data. So any data which relies on the results of a previous operation, which basically makes it dependent data, would not be suitable in parallel processing. The data used will have to go through the same processing which requires this independence from other data. Parallel processing overcomes the von Neumann bottleneck. Now, what is the von Neumann bottleneck? If you think back to the traditional single set CPUs, our CPUs are much more faster and they are waiting around, they're idling for data to arrive from the slower RAM or even cache memory. So since data has to be constantly moved between memory and processor, this leads to latency. And as processor speeds have increased over time, the amount of time that processors idle has also increased. And since the processor's performance is limited to internal data transfer rates along the buses, we need to find a way around this particular issue, and parallel processing helps us with that. Now, the bottom line is that it doesn't really solve the von Neumann bottleneck, because that means that the memory is on one side and the processor is on the other side, and there's a slow bus in between. But it does help improve the performance because you're now getting an instruction broken down, which means that they're probably quicker to transfer, and then they're being processed by multiple processors. Those processors are operating at the same speed as other processors, so a lot of performance gains are possible. However, parallel processing requires more expensive hardware, so when deciding whether or not to use this type of processing, it is important to take this factor into account as well. Okay, let's move on to grid computing or parallel computer systems. Then how do we actually create these parallel computer systems? So SIMD and MIMD are the most commonly used processors in parallel processing because you're working with multiple data sources. A number of computers, mostly containing SIMD processors, can be networked together to form a cluster. The processor from each computer forms part of a larger pseudo-parallel system, which can then act as a supercomputer. Now, do remember, supercomputers are specific machines that will have multiple processors inside them. We're not talking about that. We're talking about creating a pseudo-parallel computer using a grid-type system. So your PC could be connected to another person's Mac, which could be connected to another person's PC, and it forms a grid, and the task is subdivided. So different parts can be given to each individual computer to speed up processing. And massively parallel computers have evolved from linking together a number of computers, effectively forming one machine with several thousand processors. And by linking computers or processors together in this way, it massively increases the processing power of the single collective machine, in effect creating a supercomputer. Now, this is subtly different to cluster computers, where each computer or processor remains largely independent. In massively parallel computers, each processor will carry out part of the processing, and communication between computers is achieved via interconnected data pathways. And these data pathways are used to transfer data between the different computers in the cluster network. Now, some common applications of grid computing involve high volume data handling. So governments, e-commerce sites, and social media sites normally use it. The movie industry also uses it for processing special effects. The gaming industry also uses it from rendering to managing server traffic. So the use of grid computing or massively parallel computers is much more varied than traditional supercomputing. And the reason for that is we can scale it up or scale it down depending on our need. So when you want a bigger network, you just add more computers to it. And when you want to scale it down, you just remove them from the cluster. Okay, hopefully you have enough knowledge now to answer some of these questions that you see on screen. So pause the video and have a go, and do share your answers with me, or do get back to me if you need further clarification on any of these questions. Okay, that's the end of today's session. Hopefully you should be able to explain SISD, SIMD, MISD, and MIMD, and perhaps what the differences between each one of these are, and perhaps the applications of some of these architectures. Going back to previous lesson as well, you should know how pipelining works. It's a very important topic. What is meant by grid computing or parallel computer systems, and how an interrupt is handled by a RISC processor. And this is another important area that we covered in the previous lesson and also at the beginning of this lesson. If there are any questions or if you're not sure of something, please do get back to me. Otherwise, that's it for now, and I will see you in the next one.